associated with the act of shaming and employed the linguistic analysis over the identity and content of direct and indirect shaming in the UNGA in general, and came out with interesting findings, not only regarding the discourse on Israel, but more generally on the tendencies of other states to use the United Nations in order to target and shame various actors in the international arena. So thank you for listening, and thanks for the DSI for funding this project. I'll be happy to answer questions if you have, and of course to promote more and more cooperation in the field of political science, which really needs some more data science tools employed into it. Thank you.
We have time for one question if anybody wants. I do want to ask one question that I think is relevant. Using the tool of Spike, can anyone use it, or do you need to be an expert with a computational sort of mindset?
You don't have to have any computational skills. You just need to have some interest in the question of how language and text is relevant to a research question.
Anybody can know?
I use it with my students. They are BA students from political science. Really, they have no computational skills, and we just practice how we can ask questions about political text and answer them just using simple buttons.
So thank you for
another quick question. I mean, do you think this kind of experience of you where you use Spike to explore your kind of text was kind of replicating maybe in other text domains, like in other disciplines?
Yes, and I think that's when you need to ask you about it, but I think that's the entire purpose of Spike, is how we can, okay. There's two answers to this question. First, I'm not a data scientist, and I have one critique on data scientists, that often the domain is overlooked. So there's a great focus on the method, on great focus on the model, but if you're not expert on the domain, you might overlook some important caveats, and our UNGA dataset is a wonderful example, because we have papers made by data scientists all around the world that analyzed and showed really cool models that I cannot understand because they are gibberish for me, but eventually they didn't take into account many important features of this kind of vocabulary, and the data has nothing to do with political insights. Okay, so they really trained really well algorithms, but they didn't provide me as a political scientist findings that I can use in my field. So that's the first answer. The second answer is I think that at the end, what we are opting for is a cooperation between domain experts that want to invite data science tools into the domain, and data scientists who are willing to cooperate with non-data scientists and creating such platforms. So yes, you can totally use, you need to have short answer, yes, no problem.
Thank you again. I wanted to say that one of the ground rules in this event is that we're not allowed to talk politics and bring it into academia, but I think that in this case we have no choice. But I'll introduce our next speaker, Amir Leshem, from the Faculty of Engineering, who will be talking about this project along with David Sarne from Computer Science, which is also funded by the sciences.
Here? Okay, thank you. Okay, so I'm going to talk about multi-agent learning with limited communication, and I'll start with multi-armed bandit, and then I will talk a bit about Markov games, and probably half of you, and I'm underestimating the number of people that don't know half of the words on this, but we will go forward. So I want to thank the DSI. Apparently it's a highly competitive research grant. We got the second prize of 40,000 shekels, so I went on and I got an ISF grant and Ministry of Science grants on the same subject, so it seems that it's very competitive. Also, Mafat funded this research, so this is not uniquely by DSI, but they contributed their share. There was also some collaboration with Vikram Krishnamurthy from Cornell about congestion games and inverse RL, but I will talk about that later. So what I'm going to talk about has applications to learning in repeated games. I'll talk about a bit about multi-armed bandit, and then I'll talk. Probably I will not have time to talk about the single controller under limited communication. So some papers, all of them are in my website. These are the journal publications. There were some in MIPS and ICML. And I want to thank my collaborators and students, Dudi, Eli Bistritz, now coming to Tel Aviv, Vikram, many others. But I don't have time, so I'll skip. Thank you all. So one interesting application of what I'm going to tell you is application to congestion games in traffic. So that's what we are doing with the Koreans. We are trying to develop the next generation traffic control techniques using limited communication between cars. So I'll tell you a bit about, I decided I'm not going to give a general talk, I'm going to go deep into the details and at least try to teach you something, so you get something out of it. So what is a multi-armed bandit problem? This is a very old problem, I think originated in the 30s, and I think all of you actually had to encounter this problem. You have multiple options. Each option has a certain value for you, but you don't know what is the value. So you try one, you try the other. At some point you need to pick the best. And the question is, how good can you do or how bad can you do? So you can do quite badly if you don't do anything, but doing it in a good way is hard. And one of the notions related to multi-armed bandit is the notion of regret. Every time that you don't pull the optimal arm, you accumulate a regret. And you want to minimize the regret, and the question is how fast the regret grows. It turns out that it can grow logarithmically if you're a single player with like multiple arms. And these are like classical results by Lyon Robbins from 1985, and then there were several extensions by Agrawal, and there were some index policies by Auer and others. So this is like a single player having multiple options. But in reality, in many cases, I'll skip the history because my time is limited. So I'm going to focus on the multi-agent case. So we have multiple players, each one has an option, and they need to share resources. For example, I have multiple jobs that needs to go to multiple computers. I have multiple cars that can take the different routes, and they need to coordinate. But they cannot talk to each other. I don't allow them to talk to each other. The only thing that they can observe is when they have collisions with each other. So whenever they have a collision, okay, I'm talking about cars, that sounds really bad. Usually I'm talking about a collision is when two agents pick the same strategy. So I'm not talking about car collisions. So whenever they have a collision, they know that somebody else wanted the same resource. And the question is this information sufficient, and what is the regret that I can provide? And the surprising result, so in the multi-agent case, there are a few options. One is that I only want to optimize my regret, and I compete against the others. So competing against the other is basically a competitive game. Unfortunately, in this game, every permutation is a Nash equilibrium. And if you don't know what it is, it's okay. But whenever I allocate one resource to one agent, I assume that I have the same number of agents and resources. It's an equilibrium. Why? Because if somebody tries to take another arm, he gets a collision, he gets 0. So he loses. So for any allocation that I give them, they should be happy. Unfortunately, many of these allocations are actually almost exponentially large number of these allocations can be quite bad. Actually, they can be, the total utility can go to 0 in certain circumstances, while they can get positive reward if they coordinate. So I will not talk about the competitive way to do that. I'm going to talk about the cooperative. So in order to cooperate, we need to communicate. So quite early in 2014, Katlil et al. And then Nayar et al., they proposed to use some assignment algorithms in order to find the optimal allocation. And the way they do it is by sharing the value between the agents. But that requires a lot of communication. The question is, can we do it without communication? And the surprising result, I think, is that a cooperative multi-agent bandit learning can be achieved with no explicit communication. Just we need to observe whenever we collided when we wanted the same resource. That is sufficient in order to get log T regret, or almost log T regret here, and I will show you that with a bit more sophisticated protocols, we can actually get log T regret, which is optimal even in the single user case. So that's pretty surprising. So we don't need to communicate in order to cooperate. We just need to decide in advance what we are going to do. So I'm just going to try to give you some of the main problems here. So one thing is that we are playing in the dark. We don't know what is the utility. We are playing a game. So usually game theory says we have a game, everybody has the... I want to walk. Everybody has a utility. He knows what is the utility given his strategy, the strategies of the others. Here they don't know. They need to learn what is the value of each action, but they don't know what were the actions of the other players. So that becomes even more tricky. How much time do I have?
5 minutes.
5 minutes, okay. So the question is, how do we do that? So the idea is that we divide the learning process into phases. At each phase, we do 3 steps. We have 3 different steps. I'll skip the frightening equations, and I'll go. So in the first step, we do exploration. Everybody just tries each of the resources. We have n players trying n resources. So on the average, we have very few collisions, and we can actually learn quite accurately. Once we learn the utilities, but we don't know them exactly because we only sample them and these are noisy. The surprising result is that if our estimates are sufficiently accurate, the optimum of the noisy utilities game is the same as if we knew exactly the utilities. And that follows from standard linear programming theory. And then what we need to do is we need to bound the probability so we need to find a mechanism for negotiation because we only can negotiate through collisions. And then by the end of the negotiation, we do exploitation for exponentially long period. And then the exploitation grows exponentially. The other phases grow